Hello everyone, welcome to today's video. I am PREETAL NILANG SHAH and I'm going to be explaining to you an important topic in the world of operating systems, virtualization. So let's take a look at today's agenda. Here's the agenda for today's video. Since virtualization is a vast topic, I have done my best to just make 7 topics for better understanding of what it is all about. So as you can see in topic 1, 2, 3, and 4, I have explained the terminologies that are related to virtualization of OS, and in topic 5 and 6, for your better understanding, I have shown the comparison between containers, virtual machines, and hypervisors. Finally, when we come to topic 7, I have explained the types of virtualizations which are present apart from OS virtualization. So let's start with the first topic. Before we move on to topic 1, I'm pretty sure everyone needs an introduction as to why do we need virtualization in the first place. Let me tell you one thing. There were a lot of limitations of x86 servers. Many IT organizations must deploy multiple servers because of this, and each are operating at a fraction of their capacity to keep pace with today's high storage and processing demands. The result? Huge inefficiencies and excessive operating costs. Here enters virtualization. Virtualization relies on software to simulate hardware functionality and create a virtual computer system. This enables IT organizations to run more than one virtual system and multiple operating systems and applications on just a single server. The resulting benefits include economies of scale and greater efficiency. So as you can see, we shifted from multiple servers to just a single server. That's the power of virtualization. Topic 1. What is virtualization? Now, virtualization is the process of running a virtual instance of a computer system in a layer abstracted from the actual hardware. In layman terms, it basically means running multiple operating systems on a computer system simultaneously. To the applications running on top of the virtualized machine, it can appear as if they have their own dedicated machine, where the operating system, libraries, and other programs are unique to the guest virtualized system and unconnected to the host operating system which sits below it. For example, the Oracle VM VirtualBox enables you to run more than one OS at a time. This way, you can run software written for one OS on another, such as Windows software on Linux or a Mac, without having to reboot to use it. So again, in layman terms, it basically means that we can run multiple operating systems on a computer system simultaneously. Operating system based virtualization is what we're going to be focusing on. So it basically refers to an operating system feature in which the kernel enables the existence of various isolated user space instances. The installation of virtualization software refers to operating system based virtualization. As you can already see from the word, operating system based virtualization, it is clearly referring to the operating system that we want to run on our host operating system. So it is installed over a pre-existing operating system, and that operating system is called the host operating system. In this virtualization, a user installs the virtualization software in the operating system of his system like any other program. Any other program, like you install Java, you install Python, the same way you can just install this and utilize this application to operate and generate various virtual machines. Here, the virtualization software allows direct access to any of the created virtual machines to the user. As the host operating system can provide hardware devices with mandatory support, operating system virtualization may affect compatibility issues of hardware even when the hardware driver is not allocated to the virtualization software. Virtualization software can convert hardware IT resources which require unique software for operation into virtualized IT resources. So as you can see from this paragraph, it basically implies that it's not like the virtual machines have direct access to the hardware, but instead it is getting the hardware as a virtualized form. So as the host OS is a complete operating system in itself, many OS-based services are available as organizational management, and administration tools can be utilized for the virtualization host management. Here you can see the image that I've put. Hardware virtualization host is our first layer, that is our host operating system. And on top of that, we have our virtual machine management, and you can see 3 VMs here. Each VM can be run simultaneously side by side, which include guest operating system and application software. Now we move on to topic 2. What is a hypervisor? A hypervisor is a program for creating and running virtual machines. Hypervisors have traditionally been split into two classes: Type 1 or bare metal hypervisors that run guest virtual machines directly on a system's hardware, essentially behaving as an operating system. To put it in more simple words, it is basically a virtualization software that has been installed directly onto the computing hardware. This type of hypervisor controls not only the hardware but one or more guest operating systems also. Type 2 or hosted hypervisors behave more like traditional applications that can be started and stopped like a normal program. To put that also in simple words, it basically means that a hosted hypervisor is installed on a host computer which already has the operating system installed. It runs as an application like any other software on that computer. Most hosted hypervisors can manage and run multiple VMs at a time. So as you can see here in this image, the two types of hypervisors are given. The first type is native or bare metal. Second type is hosted or embedded. So you can see here that in native or bare metal, first layer is hardware. Then we have our hypervisor, and then we have our two operating systems that we are running side by side, virtual operating systems. And then coming to the type 2, that is hosted or embedded, you can see now we have our hardware, and there's no direct contact to the hardware. After the hardware, we have our host operating system. Then we have our hypervisor, and then we have the two virtual operating systems that we wish to run. So the first image is also for your understanding, where hypervisor kind of behaves like an intermediate layer between, the hardware and the virtualized operating systems. So in modern systems, this split is less prevalent, particularly with systems like KVM. KVM is basically the short for, kernel-based virtual machine, and it is a part of the Linux kernel that can run virtual machines directly. Although you can still use a system running KVM virtual machine as a normal computer itself. How do hypervisors work? Hypervisors support the creation and management of virtual machines by abstracting a computer's software from its hardware. Hypervisors make virtualization possible by translating requests between the physical and virtual resources. Bare metal hypervisors are sometimes embedded into the firmware at the same level as the motherboard basic input-output system BIOS to enable the operating system on a computer to access and use the virtualization software. You might have come across the word virtual machine. At the moment, you might be confused as to what a virtual machine is, but do not worry because in the later slides, I will be clearing that. So coming back to how hypervisors work, in this image, you can see how type 1 hypervisor and type 2 hypervisor has been represented. In the previous slide also, we have discussed about the diagrammatic representation, but this might also help for better understanding. So we have in type 1 hypervisor, we have the hardware, then we have our hypervisor, and then we have the virtual OS attached to the hypervisor. And then we have type 2 hypervisor with the hardware, but no direct attachment of the hypervisor. Instead, after the hardware, we have our host operating system, then the hypervisor, and then the virtual OS. Why do we need a hypervisor in the first place? Like I explained to you, hypervisor is an intermediate layer between the hardware or the host operating system and the virtualized operating systems. Hypervisors make it possible to use more of a system's available resources and provide greater IT mobility since the guest virtual machines are independent of the host hardware. This is a very important line. The guest virtual machines are independent of the host hardware. This means they can be easily moved between different servers. Because multiple virtual machines can run from one physical server with a hypervisor reduces space, energy, and the maintenance requirements. Now we move on to topic 3. What is a virtual machine? We had encountered this word in a previous slide while I was talking about hypervisors, and now we can see what a virtual machine is actually. The main purpose of virtual machines is to operate multiple operating systems at the same time from the same piece of hardware. Without virtualization, operating multiple systems like Windows and Linux would require two separate physical units. But with virtualization, this is easy as we can run multiple operating systems side by side from the same piece of hardware. So virtual machines may have access to any number of resources: computing power, through hardware-assisted but limited access to the host machine's CPU and memory, one or more physical or virtual disk devices for storage, a virtual or real network interface, as well as any device such as video cards, USB devices, or other hardware that is shared with the virtual machine. Now, if the virtual machine is stored on a virtual disk, this is often referred to as a disk image. This is also another important term, disk image. A disk image may contain the files for a virtual machine to boot, or it can contain any other specific storage needs. As you can see from the picture here, we have our first layer, which is the computer's hardware. Then we have our host operating system, and then of course we have our hypervisor. Like I said before, it's always there. And then we have three virtual machines created here: virtual machine 1, virtual machine 2, virtual machine 3. And each virtual machine will contain the guest operating system and its applications. And so clearly you can see how multiple operating systems are running side by side by using just the same piece of hardware. How do virtual machines work? As you can see, I have written a very detailed explanation of how virtual machines work, but it's actually quite simple to understand. So let me just explain it to you. A virtual machine is a computer file, typically called an image, that behaves like an actual computer. So in other words, you're creating a computer within a computer. It runs in a window, much like any other program that you open or you run on your system, and it gives the user the same experience on a virtual machine as they would have on the host operating system itself. Now, one question that a lot of people have is, if there are changes made on the virtual machine, or if any file gets corrupted on the virtual machine, will there be any changes made on the host operating system? The answer is no. There will be no changes affecting the host operating system. As you see, the virtual machine is sandboxed from the rest of the system, meaning that the software inside a virtual machine can't escape or tamper with the computer itself. This produces an ideal environment for testing other operating systems, including accessing virus infecting data, creating operating system backups, and running software or applications that the host operating system wasn't originally intended for. Multiple virtual machines can run simultaneously on the same physical computer. For example, the image that you have seen in the last slide, I have shown how three virtual machines were running side by side on the same piece of hardware. So for servers, the multiple operating systems run side by side with a piece of software called Hypervisor to manage them, while desktop computers typically employ one operating system to run the other operating systems within its program windows. Now, each virtual machine provides its own virtual hardware, including CPUs, memory, hard drive, network interface, and other devices. The virtual hardware is then mapped to the real hardware on the physical machine, which saves costs by reducing the need for physical hardware system along with the associated maintenance costs that go with it. Plus, it reduces power and cooling demand. So the last line is important, that each virtual machine provides its own virtual hardware. As you can see, There's no direct access to the hardware. Everything is becoming virtualized, and then the virtual hardware is mapped to the real hardware, which saves the cost by reducing the need for the actual physical hardware system along with those operating systems. Now, the benefits of virtual machines are many, but here we can see 5 of the best benefits of a virtual machine. First, operational flexibility. As you can see here, there are 3 different OSs. Operate separate instances of multiple OS types. Basically, it means that it can run multiple OS side by side. Then we have reducing overhead. Run multiple virtual machines on the same underlying hardware. Reducing overhead would probably mean that for each operating system, we do not need to take a different, set of system. You can just you can make it run on the same underlying hardware. Centralization. Consolidate systems to simplify management. Scalability. Easily scale your virtual environment as your business grows, and disaster recovery. Restores data and system states from the VM instances. Move on to topic 4. What is a container? Containers are a lightweight, more agile way of handling virtualization. Rather than spinning up an entire virtual machine, a container packages together everything needed to run a small piece of software. A container is basically a standard unit of software that packages up code and all its dependencies so that the application runs quickly and reliably from one computing environment to another. As you can see in the image given, above the host operating system, you can see something called a Docker. A Docker container image is a lightweight, standalone, executable package of software that includes everything needed to run an application: code, runtime, system tools, system libraries, and settings. This all is included in that one Docker container image. So container images become containers at runtime. And in the case of Docker containers, images become containers when they are run on the Docker engine. Available for both Linux and Windows-based application, containerized software will always run the same regardless of the infrastructure. Containers isolate software from its environment and ensure that it works uniformly despite differences, for instance, between development and staging. Containers use a form of operating system virtualization. Put simply, they leverage features of the OS to isolate processes and control the process's access to CPUs, memory, and disk space. So again, in the image, you can see we have our infrastructure or hardware, then we have our host operating system, then we have our Docker, which contains the containerized applications, app A, B, C, D, E, F. Now, why use a container? So here I have listed the advantages of using a container. First, less overhead. Containers require less system resources than traditional or hardware virtual machine environments because they don't include operating system images. Second, increased portability. Applications running in containers can be deployed easily to multiple different operating systems and hardware platforms. Third, more consistent operation. DevOps teams knows applications in containers will run the same regardless of where they're deployed. For those of you who don't know what DevOps is a set of practices that combines software development and IT operations. It basically aims to shorten the system's development lifecycle and provide continuous delivery with high software quality. Then we have a fourth advantage, greater efficiency. Containers allow applications to be more rapidly deployed, patched, or scaled. Fifth advantage is better application development. Containers support agile and DevOps efforts to accelerate development, test, and production cycles. Now, DevOps is complementary with the agile software development, and several aspects of it came from the agile methodology. That's why in the last advantage we have mentioned that containers support agile and DevOps. We have learned about containers and virtual machines. We can move on to topic 5, container versus virtual machines. It will give you a brief understanding of how and when to use a container and when to use a virtual machine and which one is better. So when should you use containers and virtual machines? So first we'll talk about containers. Containers can be useful for the following points. First, enabling microservices and DevOps. Containers are at the core of DevOps and microservices. If you are in an environment that embraces the DevOps methodologies, containers can often help. This is because they're portable and fast. Like we'd already discussed, portability is a major advantage of containers. Second, web applications. Many web apps are moving to a microservices approach. If you're building web applications, moving to a microservices architecture that leverages containers have a lot of upside. Environment where speed is a must. Containers boot significantly faster than virtual machines. This enables faster testing and recovery when a reboot is required. If all else is equal and you need something fast and lightweight, go with a container. Now coming to virtual machines, it often makes sense to use virtual machines for the cases given below. Maintaining consistency and compatibility in existing environments. Simply put, many environments simply aren't using any containerization today. Servers run as virtual machines and they may be not enough compelling reasons to move away from that. In those environments, pushing a shift to containerization might not make business sense yet. Running multiple applications together. Sometimes you simply need a server or a computer to run multiple apps. Virtual machines fill this need. Third, ensuring complete logical isolation. Remember, containers installed on a given host operating system all share that kernel. From a security perspective, that is a little compromised and they are not as logically isolated as virtual machines. If isolation is important and you're choosing between VMs and containers, virtual machine may be the right choice. So now that we have discussed the difference between containers and virtual machines and where they can be used, let me just give you a brief summary again so that you have better understanding of this topic. So a lot of people confuse container technology with virtual machines, and although there are some basic similarities, they are very different from each other. Virtual machines run in a hypervisor environment where each virtual machine must include its own guest operating system inside it, along with its related binaries, libraries, and application files. This consumes a large amount of system resources and overhead, especially when multiple virtual machines are running on the same physical server, each with their own guest OS. On the other hand, each container shares the same host OS or system kernel and is much lighter in size, often only in megabytes. This often means a container might take just seconds to start versus the gigabytes and the minutes required for a typical virtual machine. So I hope that you have a clear understanding of the difference between containers and virtual machines. Now let's move on to the next topic. We have topic 6, container versus hypervisors. As you've already seen the difference between container and virtual machines, so you might be knowing a little about how the container works. But how does it compare to hypervisors? Let's find out. Containers versus hypervisors. Like we've already discussed, a hypervisor is one of the two main ways to segment a physical machine into multiple virtual machines. The other significant method is to use containers. A hypervisor segments the hardware by allowing multiple guest operating systems to run on top of it. Like I said, it is an intermediate layer. And in a container system, the host operating is itself divided into multiple containers, each running a virtual machine. So each virtual machine thus not only shares a single type of operating system, but also a single instance of an operating system, or at least a single instance of a kernel. Here we have an image of virtualization using containers and virtualization using hypervisors. As you can see in virtualization using containers, we have our hardware, then we have our host OS kernel with the virtualization layer, and then we have our container 1, 2, and 3 containing different applications. All of them are sharing a single instance of the host operating system or a single instance of the kernel. Now, virtualization using hypervisors, we have our hardware, then we have our host operating system, then we have our hypervisor, and the hypervisor has managed to make multiple operating systems run on top of it. So we have our virtual machine 1, virtual machine 2, and virtual machine 3, each containing application, virtual hardware, and guest OS of its own. Containers have the advantage of providing lower overhead and thus increased virtual machine density and are often more efficient, particularly in high input-output environments. However, sometimes they might restrict the guest operating systems to those run by the host. It is not possible, for instance, to run Windows inside a container on a Linux operating system, and the isolation between virtual machines is in general poorer. Further, if a guest manages to crash its operating system, for instance due to a bug in the Linux kernel, this can affect the entire host because the operating system is shared between all the guests. As a result, the performance and maturity of a hypervisor is much more important to consider. Now we have come to the last topic in today's video. Topic 7, types of virtualizations. The virtualization that we just discussed is an OS-based virtualization, and it is just one of the many types of virtualizations. So let's take a look at the other types of virtualizations present. We first have application server virtualization. It is often referred to as an advanced load balancing as it spreads the applications across servers and servers across applications. This enables the IT departments to balance the workload of specific software in an agile way that does not overload a specific server or underload a specific application in the event of a large project or change. In addition to load balancing, it also allows for the easier management of servers and applications since you can manage them as a single instance. Additionally, it gives way to greater network security as only one server is visible to the public while the rest are hidden behind a reverse proxy network security appliance. Now that we have discussed application server virtualization, let's move on to the application virtualization, which is, often confused with the application server virtualization. So let me just explain to you how they're different. So what application virtualization means is that applications operate on computers as if they reside naturally on the hard drive, but instead are running on a server. The ability to use RAM and CPU to run the programs while storing them centrally on a server, like through Microsoft Terminal services and cloud-based software, improves how software security updates are pushed and how the software is rolled out. We now have administrative virtualization. Administrative virtualization is one of the least known forms of virtualization, likely due to the fact that it's primarily used in data centers. The concept of administration or management virtualization means segmented admin roles through group and user policies. For example, certain groups may have access to read specific servers, infrastructure, application files, and rules, but not to change them. Now then we have hardware virtualization. Hardware virtualization is one of the rarer forms of virtualization, and when simply explained, it is like OS virtualization. It is in fact often required for OS virtualization, except instead of putting multiple software instances on a single machine, chunks of a machine are partitioned off to perform specific tasks. Storage virtualization. Storage virtualization is an array of servers that are managed by a virtual storage system. The servers aren't aware of exactly where their data is and instead function more like worker bees in a hive. And the last virtualization is network virtualization. Network virtualization involves virtually managing IPs and is accomplished through tools like routing tables, NICs, switches, and VLAN tags. So with that, we've come to the end of the different types of virtualization. I have explained each virtualization just in brief, as the main topic of our video was OS-based virtualization. So feel free to, check up on Google about these virtualization techniques, but I hope you have understood what each one does. This brings us to the end of our video. I hope I have given you a much clearer idea of OS virtualization and all the terminologies connected to it. Let's take a quick recap. We first learned why we needed virtualization in the first place. Then we learned about virtualization. Then we learned more about containers, hypervisors, and virtual machines. For your better understanding, we also saw the difference between containers, virtual machines, and hypervisors, and we finally saw the different types of virtualizations present other than the OS virtualization that we discussed about. So hope you liked this video and hope it cleared your concepts. Thank you.